Okay, great. Looks like we're live. In this video, I'm going to continue work on this schematic, and I'm looking through ways to improve the EMI performance of this schematic. I've actually been trying a little bit of a new approach on this one because I want to kind of get to the point in KiCad where I can reuse a lot of the building blocks of schematics that I want to use often. I want to put them into separate sheets so that I can just reuse them. And this has proven to be a little bit hard in KiCad because KiCad doesn't seem to have that kind of workflow in mind. So, for example, I can have the sheets in a sub-repository in the same directory where I have my project. But when I re-annotate the schematic, then all the annotations of the subsheets change instead of having all the annotations in the top-level directory. So that's a bit annoying, but it seems to work for now. So I'll just leave it like this, and we'll see if I can figure out a better way to do it as I work through this schematic. But it's actually pretty nice to be able to reuse building blocks. Like, for example, I have the CPU building block. I can just take this to a different schematic and build upon it. So more stuff like that in KiCad. That's something that I really want to see, and that's also something that I would add if I get to the stage of adding more modifications to KiCad, which is a bit annoying as well, because every time they release a new version, I have to solve all of the merge conflicts. But anyway, what we need to do on this schematic is make sure that any of the EMI radiation doesn't get out, and any kind of EMI radiation that this board is going to be subjected to doesn't get in. And the more I looked into it, the more I realized how little I know about EMI. I can kind of grasp the general concept, but actually figuring out what values for the components to choose, that gets a bit complicated, because number one, I don't actually know all of the properties of this circuit until I actually have built it, and until I actually have a board that I can test. And number two, it does get a bit tricky, because there are things when it comes to EMI. For example, we could do it like this. Let's see. We have two basic filters. We can have a common mode filter and a differential mode filter. So let's see here. Can we put this CM? Yeah, we can use this one. Use this one for now. So if I place the common mode filter there, this would be, the purpose of this would be to filter out any noise that comes from, for example, a mobile phone that is being held like close to this device. Now, in order to kind of make this into an LC filter, we have to realize that any disturbance that comes in on the input here is going to be referenced to ground, because quite naturally you're holding your mobile phone, and it's not actually connected anywhere, but it's kind of referenced to earth, to ground. And we're going to be keeping earth separate from the circuit ground. So on the circuit, we'll have ground that spans all of the ground pads and all the ICs, but that's going to be ground that is local to the circuit, and then that ground is going to connect to the chassis, which will connect to earth, in theory. And to do that, we have to put two capacitors here. So we can do like this. 100. I can choose a 100 nanofarad capacitor, and I can put it here, and another one. Let's see. Put this one here. And I can put another one there. And then we connect the middle point here. So the middle point between these capacitors is going to be the chassis ground. Let's see, GND. Use this symbol for the chassis ground. Now, the mounting holes are not going to be connected to the ground. And we can either make the mounting holes non-plated holes or connect them to the chassis ground. So if we make it this way, let's say we have a, let's say we do like this. So this would be a common mode line filter. So if there is noise coming in from, let's say, some kind of radio interference, because this is going to be connected to the battery, right? So if we go back here, we have a connector here. So this connects directly to the cable. So this goes to the battery or any kind of power supply. And if there is noise coming in here that is referenced to ground, then it's going to be filtered by this. So the two coils on this common mode choke with the capacitors basically form two LC filters to ground. So the signal goes, it's always in phase. So when it's common mode signal, it's going to be in phase. Differential signal is always going to be out of phase. So you can have, we can see, for example, a single signal line can be thought of as a differential mode signal. But in common mode, they're going to be in phase, and they're going to be both filtered through this choke and through the capacitors and to ground. Now we can also, and this is the interesting intricacies of this type of stuff, which I don't fully understand yet, which I'm kind of in the process of learning. And it's that we can have, for example, so we can make another filter here. We can have, let's see, we can have, we can have two ferrite beads, or this should actually be an inductor. This definitely should be an inductor. So let's see. Let's take a coil, and this is just an example because I don't think I'm not doing actually any calculations on this, which I should be. But let's just pick a coil. So let's do like this. And let's just take any coil here. So let's say I put a. Okay. Let's see. I need to restart this. I wonder if my camera doesn't have any battery left. Yeah, the camera has no battery left. So fuck the camera. Let's do this without the camera. Okay, so I can place a capacitor here then, and obviously I should be calculating this, but right now I'm not calculating this. And this forms another LC filter, which would be for the purpose of filtering differential mode noise. So if there is a signal here that is noisy and the ground is at 0, then we'll be filtering that signal. Now, there's another thing here that these two lines, they need to be balanced. So we should divide this coil by 2, and then place another coil here, which is half of the inductance. But the thing with the way it seems to be in reality is that you never see this kind of configuration in circuits, in final circuits, because this thing actually has leakage inductances which simulate the behavior of these inductors. So this common mode choke actually replaces the differential mode filter that you will be putting here. So we can remove this, and we don't have to worry about them, and we can just worry about the common mode choke. So, and the next question is like, obviously, what should I be filtering? And I've been sort of reading through various materials. Like, obviously, we have the known frequencies. Oh, there's another thing, by the way. The output impedance of this filter has to be less than 10 times the input impedance of this one. So we have to check ACT 4088. Let's go to the datasheet and check what the input impedance would be on this one, so that we know. Let's see, ACT 4088. Because if it is more than 1/10 of the input impedance of the buck converter, then we are likely to get instability in the buck converter. And I think that the net effect of that is something I've seen before, is that the buck converter can actually go into this unstable mode. So it will just sort of buzz or go like bzzz, in a very high-pitched tone, and that can sometimes lead to circuit damage and all kinds of things. So we really don't want to have the impedance higher than 1/10 of the input impedance of the buck converter. And there is a formula somewhere also that, let's see, maybe this one actually describes input impedance. What would be the input impedance? There is a formula, though, that can be used, that I've seen, that can be used to calculate the input impedance of the buck converter. So as I said, I'm kind of like parts of this. I'm not really. I wouldn't say that I understand. I wouldn't say that I understand the details, all the details that go into this, because it seems to be a very it's a very deep subject. There's a lot of little details that you can't really. Like it's the kind of subject where you can measure things, you can calculate things, but then you have to also answer the question: is what I'm measuring actually the correct quantity to measure, or like is what I'm calculating actually going to be the real behavior of the system? And at this point, I don't know, and that's why I have to learn more about this. And if you're an EMC engineer, you're welcome to comment and tell me exactly where to find the relevant information. But for now, I'm going to look up this formula. So input impedance of buck converter. Oh, God damn it. This is me trying to simulate an LC filter, which I'm, by the way, not happy about because I didn't get the result that I was expecting. Let's see. Firefox. Come on, Firefox. There we go. So, input impedance of buck converter. And it's definitely not as like, oh, this is actually input filter design. I think this was the one I posted on my Discord. Let's see. Let's have a look at this. And also, like, you cannot just reuse something that worked on a different circuit, because there's always different frequencies that you have to filter. So the way it seems to me is that there's actually no way around sort of building the circuit for the first time, then testing it, like measuring the emissions of that circuit, and then coming up with filter components. Because it seems that I cannot get all of the details just by looking at the data sheets. I can sort of make a guess. I could design a filter that that kind of would be designed to handle the most likely frequencies that would be giving that would be giving problems. And I can also do things like I can try to eliminate as much as possible the kind of the expected interference. For example, I can slow down the edges of any kind of serial signals. Make them a little bit smoother without degrading the data rates. For example, if I have something that has a slow data rate, I can obviously filter the edges so that they are much more smooth, and the transmission can still continue as it should. But slowing down the edge of the signal will remove the high frequency harmonics that will be coming out of the device otherwise. And obviously, all of the like serial lines should have ferrite beads on them, yeah. So ferrite beads, they would be filtering the current slope in the signal line, which lowers the interference, because it is the current that induces voltages in things that are placed close to the circuit. But this is okay. So this is a document about designing the input filter, and design the input filter for DC circuit. So let's have a look at this. See what we can figure out from this. Input filters are widely used in power design. I have this horrible cold that won't go away. Like, when you have kids, they always bring something from the kindergarten, and you always get it. Because there's just so many different things. Like, you always get something. The kid brings home like 20 different diseases, and you get one of them always. Doesn't matter. It doesn't matter how well your immune system is able to take care of all the diseases, but you'll always get something. It's only a matter of time. Let's see. Open loop, small signal model. Yeah, so let's see. So Z filter and Z in. Does it mention that it's supposed to be 1/10? So yeah, and this is also something we're trying to filter out. We don't want to have any kind of interference going back to the power lines, and without the filter, it's likely to happen, which is going to be tested for this PCB. So nothing from the switching converter should be getting out, or at least not too much of the noise should be getting out. So with this, the devil is really in the details, like all the little details of calculating exactly what type of, exactly what inductance and capacitance value to use without destabilizing the buck converter. Because the risk here is that if I choose the wrong, values for the capacitor or the inductor, I can actually end up with an unstable circuit. Let's see here. If I choose the wrong values for these components here, I could actually end up with an unstable circuit. And so it's important to at least have some kind of idea of what the values here should be. And so let's have a look at this doc in more detail. And then I have to go back to the datasheet as well and see if the datasheet gives me any kind of information I can use. Right, this is useful. I'm just curious while I'm at it. Let's see. What is the lowest voltage on the N pin? Right. So is it 1.24 volts? Okay, can be from 112 to 136. Hysteresis is 100 millivolts. Okay. So 124. That means that let's see what this will be. So 10. So this will power on at around 6 volts, I think. Actually 8 volts, something like that. Like 7 volts. Yeah, so around 7.5 volts. When the input reaches 7.5 volts, this will enable the buck converter, which is fine because that's exactly what we want since we are getting 5 volts on the output. And I'm also placing the TVS diodes so that just in case this thing just outputs full voltage out, I wouldn't burn the circuitry that's connected to this 5-volt rail because the over voltage will go through the TVS diode and will go to ground. Okay. So I wonder what that formula is, though. There was a formula somewhere that involves the efficiency. Let's see, maybe this one gives us the formula. Where is Z in? Can we get Z in? Where can I find the input impedance of this buck converter? This is annoying. I want to at least know. Right. So what I'm building? I'm building a small circuit right now that is going to be controlling a lamp over RS422. So it's a very simple circuit, but I still have to have a microprocessor on it, and I still have to have. Let's see. Let's go out of this. I still have to have the hardware for the RS422, and also I'm using the button debouncer and overvoltage protection for buttons and switches. So this is going to be like a small control panel that's going to be sending commands over RS422 to another device. No, it doesn't support violent feminism, unfortunately. It has no philosophy at all. It cannot think. It only has 128 kilobytes of ROM. Right, so I'm going to go back to this. Let's see. I'm going to go back here. I'm going to try to find what would be the input impedance. So ZP, is that the impedance of the power source? Did I miss that? Yeah, so this one, ZP seems to be the impedance of the converter. Let's just have a look where it actually states that it is the impedance of the converter. Yeah. Based on this, it sort of seems like it's impedance of the converter. And the impedance of the source, so including the input filter, has to be much less than the impedance of the DC-DC converter. Okay, right. So actually go ahead and define the ZP here. Why I use CM choke for input? Because I need to filter out any kind of interference that's common mode interference that comes from the battery cables. And CM choke is the way that I came up with doing it. Like, unless you have a better idea. But as I said, I'm probably going to have a much better understanding of this once I can see some actual measurements of how this board performs in like an EMC chamber. But right now, I'm sort of kind of trying to make the best possible guess of what is going to be happening, and I think it's better to have a little more options at filtering out any kind of noise, both noise that comes out of the device and noise coming into the device. And then the actual tests will show how well it performs. And this type of filter is actually necessary. It's not as simple as just having a CM choke, but I've seen products that without a proper input filter, they wouldn't pass the necessary certifications for EMI emissions. But with a filter, you kind of get the proper the good performance, both in terms of stuff coming out of the device. So, for example, when this device is switching internally, you want to filter out any noise that would potentially be coming out, and also you want to filter out any noise that could potentially be coming in from the power lines. And yeah, and a good way to understand it is kind of like if you hold a mobile phone, you know, like when you hold a mobile phone near a radio, you can kind of hear the radio. You can hear the interference in the speakers on the radio. And because this interference is coupled to ground, when it gets into both power lines, both the ground, so the ground on the power lines is not actually the same as earth. And because the interference is referenced to earth, you kind of get the noise actually gets into the circuit and affects the circuit, and tries to get out from the circuit through the chassis and back to earth. So you can have actually a noise that comes into the circuit on both the ground and the power line, which would be the common mode noise coming into the circuit, and then it would do its work and disturb the circuit and then come out through the chassis. So it's not going to be coming out to the ground, to the like ordinary battery ground. It's going to be coming out into the chassis and then into the earth ground. That's where it's going to be trying to come out. The way I understand it, but I could be wrong. So I guess the next challenge is to figure out how exactly to apply this to this particular buck converter. Let's see what frequency I'm running at. .4 megahertz. So quite likely this filter is going to have some substantial impedance to 1.4 megahertz, which is likely to come out on the power lines. And for the RS422, I'm also using common mode chokes to filter out any noise coming in here through these wires. I could also possibly place capacitors there. I have to think, unless this one already has some kind of input filter. And for the buttons, I have the ferrite beads. So the idea with ferrite beads is to limit the slope of the current when you toggle the switches. So you get less noise emission because the current slope is much slower. Okay, so 1.4 megahertz. Is that the best I can come up with? So one alternative way of actually implementing this circuit, and even if I cannot 100% figure out the exact values of the components, so what I could do is essentially just make sure that I have enough places where things can be soldered onto the board, and then once the board is finished, somebody who has a very long experience with EMI emissions, who actually will be doing the testing, can then come up with suggestions on the actual values of the components. So that's one way to proceed when you're making a circuit and you cannot really, like, you kind of understand the idea, but you cannot really figure out all the details 100%. One way to mitigate that is to just place. It's better to place more components. It's better to place more placeholders for components. I could even place some placeholders for inductors here, and maybe the differential mode filtering here, because once the PCB is completed, it's possible then to experiment with different components and take some measurements also on the noises that are actually coming out of this thing, and to calculate, to do actual calculations then for the filter and for the values of the components, to make sure that the whole thing remains stable under a wide range of operating conditions. But I still want to figure out as much as possible. Maybe I can find some more information in this datasheet that could be relevant. Yeah, this is for EMI, because for this particular project, EMI is very important. So I agree that otherwise it would be a bit of an over-engineering effort to put all the chokes and all of the filtering on the board. But in this particular case, it's very important that it doesn't emit any kind of significant interference. So it has to be as quiet as a dead rat. Two microfarads. Do I use 22 microfarads? Yes. BAT54 is probably the best diode around. It's so versatile, so useful in all kinds of applications. That's good to know. So at 28 volts, I would be loading the N pin to 4.67 volts, which is below that threshold anyway. 24 volts is going to be the standard power supply for this. Okay. So they suggested I put a diode there and then connected 2V out. Note taken. Oh, actually, we should be using a BAT54 there. Might as well use the same diode. I think they're probably similar in price. Although this one is a bit bigger. Yeah, could use this one. This one is smaller, so it's better. It's a bit of an overkill to use the big one. Okay, so not much information here. So I'm not gonna spend too much time on this. I'm gonna continue with placing the remaining components. I need to place a connector here for the RS422. For that connector, I'm going to be using GST connectors, and there is a very nice connector called the JSTGH, 1.25 millimeters. Very nice connector. From the GST company. So for this, I will need, for the RS422, I would need at least 5 pins. The question is if I if I should use a 6-pin connector. What's very nice also here with GST is that they also provide the 3D models for the connectors, so I can just download whatever 3D model that I need, and I can then generate step files from KiCad, which is very practical. But the question is, should I pick the 5-pin or the 6-pin connector? I think I would only need 5 pins. Maybe even only 4 pins, but I would actually have a ground connection on the connector as well, so I can use 5-pin connector. Although if I need to use a 6-pin connector somewhere else here, then I would use a 6-pin connector, but I don't think so. I think that this is going to be the only one connector. All right, so let's add this connector to the library symbol editor. So symbol editor. Don't really. I'll just reuse one of these other symbols that I have. Let's see. Yeah. Let's just reuse this one. So this is going to be a vertical 5-pin. And I think I'm going to just name it also RS422 because I'm going to be adding some silk screen as well for the pinout, so might as well just call it RS422. And then we'll just do it like this. Grid settings, set that to 10. That's good. Oh, that's better. I think I'll put the TX here. So I'm going to call this output. And then it'll be TXP. Drag this edge here. This will be output TXN. This will be input. No, obviously it's the other way around. This would be input because it's input to the connector. XN and ground. All right. And ground is going to be passive. Okay. And next, I'm gonna just open up the footprint editor. Let's have a look. I don't think GST connectors are available in the default KiCad libraries. At least I don't think so. Let's have a look at the chat. So I'm glad you're happy to see me. I'm happy to see you too. Yeah, a lot of programmers do that as well. Just copy paste and never learn anything in the process. Yeah, always good to know why you're placing some component on a circuit board, especially when something goes wrong. If you just copy paste, you will never know what the problem is when something goes wrong. So I don't think that GST connectors are available in any KiCad default libraries, so I make my own footprints for them. So I just go to, let's see, here, and I can start with this other one that I created. So I have GST connector. Where's my GST connector? It's like, it starts with a B. There we go. That's the one. And then I just duplicate this. I guess we could just copy and interesting. Is there no paste? Oh, maybe I should do like this. Paste. There we go. So where is it? There we go. And this would be the 5-pin connector. So this is going to be just from the datasheet of the GST connector. We can go to the GST connector datasheet. I think it was here. And we can just have a look at the measurements. So it doesn't seem to be that there doesn't seem to be any difference between the vertical and the horizontal one in terms of footprint. As far as, or actually, yes, actually there is a difference. I'm just being stupid. I didn't see that it was 2.8 there and 2.7 there. It's not a big difference, but it's still a difference. So let's have a look here. This one is going to be a vertical one, I'm thinking. Yeah, I will use a vertical one for now. So I just need to extend it. And I can do like this. And I'm just gonna I'm gonna try to move this so that I don't have to do the measurements twice. So there's 125 between the pins, so I can move it, let's say 3 times 125, so 375. Let's see, I can press space and move, and then move this one 375. Kind of like that. Seems okay. And then I can just do like this. There we go. And then I can just copy these pads. Duplicate this pad. I can press space in KiCad, and then I can just place it 125 to the side. And Control D to copy, and then 125 to the side. 125. Yeah, seems okay. This would be 2. And actually, there is a function for this. It's like renumber pads. No prefix, number 1. So then we go 1, 2, 3, 4, 5. There we go. And from what I have seen in the data sheet, let's see, press escape to cancel or double click. Oh, interesting. 5. There we go. I can say that I pressed escape more than once, because I'm so used to doing that in Vim. I press escape and then I have to renumber all the pins. Like, imagine you have a big chip with a lot of pins, and then you just go and click on every one of them, and you number them, and when you're done, you just press escape as a habit, and then you have to do it again. So this will go there. I can put some, let's see, I can put a silk screen also. So this is going to be actually an RS422 connector. We can just copy it. I think this was done. So let's do like this. Let's copy this one and then paste it. And then I'm going to rename this one to RS422. So we have a separate footprint for the RS422, and then we can add a silk screen here with some text that will show what pins, which pin is which. Which is very useful. When you find that you spend more time looking up pinouts than when you find that you spend too much time looking up pinouts, you realize that it's actually very useful to have this type of silk screen on the connector. Okay. And let's just double check this. So I can see kind of that it's not centered. I'm going to center it. It doesn't really matter. This is just aesthetic changes. But we do need to check that the measurements actually match. So we have the vertical one, 2.8, 3.9. So we're looking at this one. So it's 2.8 is the size of this pad. And we have to check the pad, not the. So this is the like what is it? It's like solder paste or solder mask keep out area. So 2.8, that's correct. And 3.9 goes to from the bottom. Like, this is really weird measurements. When they measure from the bottom of this pad, and then they measure to the beginning of this pad. 3.9. Yeah, looks correct. And next one is 5.6, which I think is correct too. And then we have 1.35 from the center of that pad to the, yeah. Okay, so we're going to check this one first. 5.6. 5.6 goes from there to here. Yep, seems correct. And then we have from here to the middle of this one, which doesn't seem correct. Or maybe it is correct. It certainly looks correct. 1.35. And then let's do this. Oh, this is totally wrong. What? Oh, of course. I'm just measuring it wrong. So from there to there, 1.35. Good. So this seems correct. And the last thing here is the 3D model. So let's see here. Is the stream still running? It certainly doesn't seem that the stream is running based on what I can see on YouTube. Maybe it is still running, but the stream on YouTube is actually frozen. I'm going to try to finish this off, and then we'll see if the stream is still running. I'm just going to download this step model. There is a little bit of like logging to do on their website. This stupid unusual license agreements and stuff. So I'm just going to place this model into the proper directory. Let's see. Fuck off. There's a window there. One of the things that I find a little bit annoying with i3 is that sometimes if you have a pop-up window, you can have another window behind it, and you cannot do anything on the pop-up window because the other window actually has focus. It is actually a higher prioritized window, but it's on the back. So you have to like move the pop-up first, and then you have to find this window on the back, and you have to close it before you can interact with the pop-up, which is a bit annoying. But beyond that, i3 is a great window manager. There's no doubt about it. So hardware, and we'll go to the library. I'm just going to save this one in 3D shapes. So let's see if we can get the model. So there we go, looking good. We just need to move it. So I'll move it over there. It's looking good. And one of the best things about these connectors is that, well, actually there are two best things. Number one, it's so easy to connect cables to them because they have this easy, like there is a tab on the plug, which is very easy to disconnect. There's no friction. You just press the tab and you disconnect the cable. And number two, you have actual solder pads here. So the connector is held in place in a very stable fashion. It doesn't easily come off the board. I think it would probably be even better if this was if these, instead of these pads, it had pins. But I guess it could pose more problems if there were pins, because having the connector like this, you can actually have even two connectors on either side of the board, and not have them interact with each other. Anyway, so I need to just move this one a little bit better in place. So let me put this. Let's see. That looks good. Looking good. And save. And then we'll go to the component and we'll choose the footprint. So we can just, yeah, the footprint, I've already chosen the footprint. So now we have this component, we can place it on the schematic. We can go here, place this on the schematic for 22, and there we go. Oh, did I place this pin on the wrong grid? Okay. I guess we need to have the grid set to like, let's set the grid to 50 or something. Grid settings. Maybe I just moved this one, let's see. Oh, that one was on grid. So I'm gonna change the grid to like 50. And make sure that the pins are properly on grid. I'm going to change back to 10 and just move this like that. Okay. That's better. And we can just connect this. Okay. It's probably more correct to have the pins like that than the position of my labels. I'm going to put the ground there. And I'm going to move the labels in place like that. So, looking good. Right. I'm not even sure if, let's see. Right. Okay. So the live stream is actually running, but I cannot see the live stream anymore. So I'm gonna finish this this schematic, go over it, review it, and we'll see how many more videos I'm gonna be making with this particular schematic. Maybe layout, but do let me know what you would find most interesting. Whether you want to see me sort of reviewing this schematic one component at a time, or if that's too boring, maybe you're more interested in actual routing and placement of the components. So let me know in the comments. So that's it for this video, and do subscribe, and I'll see you later.